Hello and good day, geometry. Your recorded lesson for this week is on CO49, talking about another type of quadrilateral. So we're done with parallelograms now, but a four-sided shape, which is a trapezoid. But first, we're going to go back and correct the homework from your square page. You can make sure that you're doing that correctly before it's actually due. So a square is a very powerful shape in that it's got all those different characteristics of all parallelograms as well as all rhombuses and rectangles. So a whole bunch of things going on here. And starting with the measure of angle MKN. MKN is right here. This one goes back to the property of a rhombus where the diagonals form at a perpendicular angle. So MKN is a 90-degree angle. You've got a right triangle there. Angle LMK, which is this one right here, that's going to be a 45-degree angle, right? And we know that because we've got the right angle here, and because the diagonals bisect each other, we know that this section, MK, is 1, which means we have a right triangle. This looks kind of like a frowning face there, but we've got a right triangle with congruent legs, which means we have a 45, 45, 90 triangles. That's how we know that LMK is a 45-degree angle, as would KLM there would also be a 45-degree angle. Next one, angle LPK. LPK is right here. That again is a 45-degree angle for the same reasons that we just got done talking about. KN, which is this section of diagonal LN, is going to be 1. The diagonals bisect each other, and so LK is congruent to KN, and so we get the 1 from that. MP is this diagonal here, which diagonals being congruent, all the four sections of the diagonals here be equal to 1, means that MP is going to be 2, going all the way across. And finally, LP. LP. So here's what we have. Okay, LP represents the hypotenuse of a 45, 45, 90 triangle with leg lengths of 1 and 1. So going back to our 45, 45, 90 special triangles, we know that the hypotenuse is whatever the leg is times root 2. So 1 times root 2 is just going to give us root 2 as a value for LP. Okay, so those are your 6 answers for that section there. Now, draw a specific square and rectangle, each with integer side lengths greater than 1 and areas of 16 units squared. I had to be so specific here with integer side lengths greater than 1 because I wanted you to all come up with the exact same rectangles and the exact same square. The only square with an area of 16 square units, how can I mess up making a square? The only square with an area of 16 square units, try that again. There we go, looks the same, is 4 and 4. Okay. And as far as your rectangle, to get an area of 16 with integer lengths, your options are either a 1 by 16, but because the lengths have to be greater than 1, I've boxed you into, get it, boxed you into a rectangle with dimensions of 2 and 8. And the question is, which shape has the longer diagonals and by how much? Okay, so there's a diagonal of the square, and here is the diagonal of the rectangle. And you can basically find each of these just by using the Pythagorean theorem, or in the case of the square, you could use 45, 45, 90 triangles. But the Pythagorean theorem, we would have for the square here, 4 squared plus 4 squared equals c squared, or 16 plus 16 equals c squared, or 32 equals c squared, and we get the root of 32 as our value for c. We will go to decimal form later because our actual question is how much longer is the diagonal of the rectangle, and so it'll be much easier to compare these in decimal form. But for now, we'll leave it just as root 32. Pythagorean theorem for this one, 2 squared plus 8 squared equals c squared. which gives us 4 plus 64 equals c squared, or 68 equals c squared, or the root of 68 as our value for c. Okay, so now to figure out how much longer that diagonal of the rectangle is, the square root of 32, I'm going to round this to the nearest hundredth here, is 5.66. And the root of 68, again, rounded to the nearest hundredth here. Whoops. Hold on. There we go. Root of 68 is 8.25. So 8.25 minus 5.66, it is 2.59 longer. Okay, 2.59 units longer, the diagonal of that rectangle. Okay, now moving on to CO49, getting to trapezoids. I mentioned at the very beginning of the video that a trapezoid is not a parallelogram, right? Your parallelogram shapes are a parallelogram, obviously, a rhombus, a rectangle, and a square. Okay, a trapezoid is not a parallelogram because it does not have two pairs of parallel sides. A trapezoid, as you probably know, most famously kind of drawn to look something like this. Okay, it does have one pair of parallel sides, but not two of them. Therefore, it does not meet the criteria for a parallelogram. It is, however, a four-sided shape, so it is still part of the quadrilateral family, right? So kind of our family tree here, you've got all the quadrilaterals, all the four-sided shapes. Under that, you've got the parallelograms, which include rhombus, rectangle, and square, right? And then you also have the shape of a trapezoid here. And the last shape that we'll talk about in this unit CO50 will be a kite, another four-sided shape, but not under the trapezoid category, not under the parallelogram category. Okay, so let me draw these lines out here. So that's kind of where we are here. We're still in the four-sided shape realm, but we have moved past the parallelogram family and now on to trapezoid. So what makes a trapezoid a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Okay? Instead of having two of them, it just has one, thus trapezoid. And it says, draw two examples of trapezoids below, label each base, leg, and pair of base angles. Like I said, the first one that I drew there is probably the most common shape that people think of with trapezoids. But even something like this, would be a trapezoid, where one side makes a right angle with the base. Most people think trapezoids have to have two slanted sides. They don't. Okay, as long as they have that one pair of parallel lines, right, then you're dealing with a trapezoid. So what are the base? What are the bases? What are the legs? And what are the base angles? So the bases of a trapezoid, you have a base here and a base here. Okay, basically your parallel sides are considered the bases. And if you think about the formula for the area of a trapezoid, which is 1/2 times the sum of B1 and B2 times the height, B1 and B2 refer to the bases. And the reason why we have B1 and B2 is because the bases of a trapezoid are always different lengths. They have to be if the two slanted sides or the two sides aren't parallel. They can't be the same length. If they were the same length, then it would be a rectangle, or it would be a square, right? Or it would be a rhombus, okay? So the bases are different lengths, and that's what we talk about when we talk about base 1 and base 2. The legs are the sides of it here. So kind of draw over my drawing here, but a leg and a leg there. And then the base angles, you've got one pair down here, and one pair up top. Okay, and I'm not meaning to mark those congruent I should do a different symbol here because I don't want to confuse anybody. Base angles here, one pair here, and base angles here, one pair there. Okay, same thing over here. Base angles, one pair there. Base angles, one pair there. Then we have our leg here, base, and base up top. Okay. Now, an isosceles trapezoid is a special type of trapezoid. An isosceles trapezoid exists when the legs of the trapezoid are congruent. Let me scroll down here so we can kind of get to our next sections here. Isosceles trapezoid is a trapezoid with congruent legs. Right? So an example, right? Those legs are congruent. Okay? And there are three theorems that kind of are associated with isosceles trapezoids. And we're going to kind of divide this into what we know and what we can conclude. Okay? So if we know that the trapezoid is isosceles, so I'll put what we know in green and what we can conclude in red here. If we know that the trapezoid is isosceles, which means it has, parallel bases by default, it always will, and then it has congruent legs, then we can conclude that each pair of base angles is congruent. So you have this pair down here will be congruent, and this pair up top will be congruent to each other as well. So if you're told a trapezoid is isosceles because you know its legs are congruent, you can conclude that each pair of base angles is congruent as well. Theorem 815, again, what we know will be in green, what we can conclude is going to be in red. Okay. This time, if we know, and we'll put our parallel lines here, if we know that just one pair, doesn't matter which pair, but one pair of base angles is congruent, we can conclude it's isosceles. Okay? We can conclude that the other pair of base angles is congruent as well to each other, and we can conclude that the legs are congruent, making it isosceles. So 14 and 15 are kind of the converse of one another. In 14, if we know the legs are congruent, the base angles will be congruent as well. 15, if we know the base angles are congruent, then we know the legs will be congruent, and thus it is an isosceles trapezoid. Okay? So if the pictures suffice for you, great. If you want to do it in words, if the legs are congruent, then base angles are congruent. Next one, kind of the converse of that. If one pair of base angles is congruent, then the legs are congruent, which means the trapezoid is isosceles. Okay. The third theorem associated with isosceles trapezoids has to do with the diagonals. Okay, so we've got our isosceles trapezoid here. We've got our congruent legs. The diagonals of an isosceles trapezoid, I gotta calibrate my board here, I think. The diagonals of an isosceles trapezoid will be congruent as well. the diagonals of an isosceles trapezoid are congruent. And that works both ways as well. If you know the diagonals are congruent, you know it's an isosceles trapezoid. And if it's isosceles trapezoid, you know the diagonals are congruent. Okay, a midsegment for trapezoids. So what a midsegment does, and I'll draw a non-isosceles trapezoid here, so get us, whoa, my goodness, get us away from that. But what a midsegment of a trapezoid does is does the same thing as the midsegment of a triangle, which if you recall, a midsegment connects the midpoints of the two sides. So roughly draw in the midpoints here, connect them with the midsegments, okay? And so in red there's the midsegment of this trapezoid, and we know that it's going to bisect each leg, okay? So those parts are congruent. And the midsegment is going to be parallel to the bases. The midsegment is always parallel to the bases. So it bisects the legs parallel to the bases, and the midsegment is half the sum of the bases. The length of the midsegment is half the sum of the bases. So if we were given values, if this was 4 and this was 14, the midsegment would be the sum, 4, 14, take half of that, the midsegment would be 9. Clearly this is not drawn to scale, but that's okay. Okay. So then the practice one over here says find the value of x. Here we're given the value of the midsegment, right? So we know that 7 is going to have to equal half the sum of the bases. So you can write that a couple different ways. You can either do half and then the sum of the bases, which is 10 plus 2x, and solve for x that way. Or you could do 7 equals half the sum of the bases, have the sum of the bases be the numerator of a fraction, and show that you're dividing by 2, because multiplying by 1/2, dividing by 2, it's the same thing. Okay? So basically, kind of doing a little bit of logic or opposite operations here, we know that we get to 7 by dividing the sum by 2, which means that the sum has to equal 14. Right? So that when we take half of that or divide by 2, we get to 7, which means that subtract 10 from both sides, divide by 2, we get a value of x equals 2. Okay? I'd ask for questions, but A, you're not here, and B, no doubt this is crystal clear anyway. So we'll just move on. Oh, that's it. That's the end of it. So your homework for Monday, when we meet together again, is going to be, let's see, on page 546. On page 546, I would like you to do numbers 7 through 9, 13 to 16, and 26, 27, and 32. I'm going to put 32 in a different color because that's a challenge question. And I'll give you a hint. It involves a quadratic equation, which you have had experience solving for x in a quadratic equation before if you took advantage for the extra credit on the test. So push yourself with that one. Remember that to solve for x in a quadratic equation, it involves factoring, and you're also looking for two solutions. Okay, but see what you can do with that one. If you end up not quite getting it, we haven't officially talked about how to solve for x in algebra class yet, so you'll be forgiven. But if you can push yourself, see if you can figure it out, it'll be a good mind challenge for you. But this homework is due on Monday. That is it for trapezoids. That is how you math. Don't forget to like and subscribe, and have a great day.